All right, before the break, we talked about PO2 as determining hemoglobin saturation. However, there are other factors that affect hemoglobin saturation. They're listed here, but again, the number one influence is the partial pressure of O2. It makes us have that S-shaped curve. But let's look at the other things that influence saturation, 2, 3, 4, and 5. Consider exercise. The physical condition of exercise, and look at those changes, 2, 3, 4, and 5. Because all of those changes occur with exercise. When you work out, you get increased body temperature. When you work out, because of the lactic acid buildup, you get more acidity of the blood. Decreased pH. When you exercise, the CO2 accumulates at a faster rate. You observe an increase in the partial pressure of CO2. There's a molecule, it's a product of non-oxidative metabolism. Anyways, it's BPG, that increases. These changes all facilitate an increase in oxygen unloading during exercise. Increased oxygen unloading. More so than this curve indicates. So what these changes do is they don't change the shape of the curve, but how it affects the curve is it just shifts it down and to the right. Causes a shift of this curve down and to the right. Down and to the right. So for example, that would look like this down to the right, something like that. Down and to the right. So what that means is, well, let's look at it this way. There's a standard for hemoglobin saturation, and it's called P50. Consider that separate from this. P50, under normal conditions, not the shifted conditions, under normal conditions, P50 is the oxygen tension that provides 50% saturation. Under normal conditions, P50 is the oxygen tension, the PO2, which provides 50% hemoglobin saturation, HB-sat. And under normal conditions, this PO2 is 27. P50 is 27 millimeters of mercury. That's how much oxygen you need to saturate at 50% under normal conditions. So I'm going to ballpark it. If this is 100% saturation, 50% is around here. 27 millimeters of mercury. Okay, that's under normal conditions. So what I'm saying is, if you shift the entire curve to the right, I won't even put a number to it. What happens to P50? How does it change? Does it increase or decrease? It increases. It takes more oxygen to saturate at 50% under these conditions when it's shifting. So think of it this way. When you're exercising, don't you want to unload better? You do. You need more oxygen for the working muscles during your workout. So this actually is desirable for this condition, but you increase P50 when you shift it. There's something called the Bohr Effect. This shifting down and to the right is called the Bohr Effect. Where you shift down and to the right, and as a result, P50 increases. I'll put that at the bottom here. Bohr Effect increases P50. You're facilitating more unloading of the O2. So it's kind of like this. I use this chair analogy. Under normal conditions, the black curve, it's kind of like you're sitting on a flat chair. You can get in the chair to load it, like hemoglobin, and you can get out of the chair relatively normally. However, if you facilitate unloading, it's like if you sat in a chair that had a slight slant down to it. It's easier to slide off that chair. You can still sit on that chair. If that symbolizes hemoglobin, it's easier to unload, so it's like hemoglobin tends to be less saturated because it's easier to get off that chair. Okay? So that's the thing about P50, and of course, if you can shift it one way, you could shift it the other way. If all of these factors were reversed, for example, let's just switch a few of them. Not BPG so much, but we kind of shift it this way. I mean, you can shift it up and to the left. I usually don't talk about that too much in this lecture, but that is a possibility. So what does that mean in our chair analogy? It looks like the oxygen tension, which would provide 50% saturation, what would happen to P50? Decreases. It takes less oxygen to saturate if you shift the other way. That means it's like you're sitting in a chair like that, and when you slide in that, it's hard to get out because you're stuck in there. You could pop out of there, but it's hard to unload, okay, if you shift the curve the other way. Let's say you're skating on thin ice, literally, and you fall in, and you're exposed to super cold water for several minutes. You pull out of there, and you're all blue. You present cyanosis. Why? Why are you blue? Because the oxygen's stuck on the molecule, it can't get off. Okay, all the curve is shifted this way. I talked mostly about the Bohr effect in this lecture. The condition of exercise, that's what we want you to do. So you can shift the curve. Normally P50 is 27. All right, so under normal conditions, let's say you're at the beach, up in the mountains, no matter where you are on Earth, you know, you're relatively fully saturated. Okay, the air you're breathing, even if it's thinner air, there's not much change in saturation. So this plateau part is good for the external respiration. Now that steep slope, let's say you're reclining at the park, or you're vigorously exercising, swimming in the pool. Well, oxygen tension gets lower, but even when you're rested at a PO2 of 40, you're about 75% saturated. 75% sat. That's still pretty well saturated. But if you're huffing and puffing, you decrease to 20, saturation drops from 75 to 40. So you're more likely to drop it off as PO2 drops when you're within the steep slope range. So just remember, the steep slope is good for the internal respiration. Now I want to put a slide in on BPG because your book doesn't mention it. Let's remember what red blood cells are your erythrocytes. And let's remember how I talked about their development, how when they're in the bone marrow, they're developing, they spit out all their organelles, and that shrinks the cell size. And the last thing they spit out is the nucleus. So they have no organelles. So their metabolism is strictly non-oxidative. We do want it to be that way. You don't want the cells to burn oxygen. Their job is to transport the oxygen, not metabolize it. Okay, normally cells metabolize oxygen. Okay, the red blood cells don't. So they do non-oxidative metabolism. BPG, which stands for 2,3-biphosphoglycerate, is one of those non-oxidative enzymes that can be measured and has been measured to be elevated during exercise. What it's doing is it kind of binds the hemoglobin that negatively affects the O2 binding. Okay? It's similar to carbon monoxide poisoning. Carbon monoxide poisoning is like CO preferentially binds to HB and not O2. Okay, that's the poisoning part. But BPG has that same slide effect. So basically what I said was for the Bohr effect, which is the shift, A or B for Bohr. B, shifted this way, a little bit down and to the right. And, so here are the shifted curves for each parameter, like for example, for normal body temp, you can see it shifts to the left in colder temperatures and to the right for warmer temperatures. And the same thing for CO2, shifts to the left when it decreases, shifts to the right when it increases. These are the parameters I listed on the board for the exercise thing. Okay, so keep track of that, the ones we noted over there. So again, just to strictly define this Bohr effect, I wrote it on the board, but here it is defined on my slides. The shifting of the oxygen hemoglobin saturation curve down and to the right during exercise. That's it. That's the effect. It facilitates the unloading of oxygen from hemoglobin of blood passing through active muscle beds. This unloading of oxygen makes it available to tissues to support their increased metabolic demands. All right? So you drop off the O2. The other thing is the CO2. We have to get that out of the tissues into the blood. And what I had said before the break, the transport of CO2 happens 3 ways. Remember I gave you that 100% is like 60 mils per deciliter. And I said 7% of that 60 is just dissolved. I think the number is 5. I said 23% binds to hemoglobin because it's carbaminohemoglobin. It's actually binding the hemoglobin. And the 70% is in the form of bicarb. Okay. So that's how we transport it in the bloodstream. So think of CO2 as a metabolic waste product that you have to extract from the tissues, and through the active ventilation or breathing, the partial pressure of this metabolic waste CO2 is kept low in your lungs, in the alveoli. So this creates a gradient for CO2 to move from tissues through the blood to your lungs and breathe it off to the air. Here's a picture of that. Tissues are accumulating the CO2. Somehow you got to breathe it off. So you extract it from the tissues, you get it into the venous blood, and the blood will transport it to the lungs, where you can finally breathe it out to the atmosphere. Now, one biochemistry equation to know for CO2 is this one here, because the carbonic acid, CO2 can affect the pH of the blood. So let me clear this off. CO2 can be wetted with water. It can be combined with water. And those molecules are pretty inert. They don't normally want to interact. They need an enzyme to make them combine faster. The enzyme is Ca, carbonic anhydrase. I don't have it on this slide. It must be on the next slide. Anyways, CO2 and water will form carbonic acid. H2CO3 is carbonic acid, which is a weak acid which partially dissociates, giving up a proton, becoming H3O3. So you got your hydrogen ions, which affects pH, and this is bicarb right here. Bicarbonate. And bicarbonate is 70% of the way that the blood transports the CO2 in the plasma compartment. Okay, so you have to know this equation for CO2. So again, carbonic anhydrase, Ca, we say it's the enzyme that wets CO2 because it combines it with water. CO2 is accumulating in the tissues, say for example a muscle cell. You can either push it into the plasma compartment directly just by dissolving it in. That's only 7% though. Carbaminohemoglobin forms by binding the hemoglobin to the carbon dioxide. That's only 23%. This equation here is the predominant way the blood transports CO2 in the blood in the form of bicarbonate. One thing about this carbaminohemoglobin, though, let me advance the slide.
Professor?
Yeah.
Is the enzyme used throughout both of those? I mean, all three of them?
No, actually the enzyme is only for this last one here. And in particular, I have two equations here. I say one is slow and one is fast. Because in the plasma compartment, there's no enzyme. That's why it's much slower. But on the surface of the RBC, it happens much faster because you have the enzyme. I'll bring up that here. On surface of RBC. So this enzyme only pertains to this equation. It does not pertain to it binding to hemoglobin or just dissolve. So here's the thing. We're trying to get CO2 into the blood. Here's gas exchange at the peripheral tissue. Here's a red blood cell. And let's say here's peripheral tissue cells. Let's say there's an increase of partial pressure CO2. I don't know, well, maybe it's 45, maybe it's higher. But you have CO2 accumulating in the tissues, and you're trying to get it into the bloodstream. Let me talk about the carbaminohemoglobin for a second. So blood's coming in, oxygen rich. Let's just say that you have your hemoglobin, 4 square circle. Let's say it's completely saturated. So I want to occupy every spot. It's like when I'm standing at the bus, stop. You know, I'm waiting for the bus. I used to take the bus when I was a grad student, and I see the bus coming down, but I see the bus is completely full. I'm like, oh dang, how am I going to get on the bus? It's full. Well, if the bus stops and people get off the bus, then there's room for me to get on the bus. So that's like this. It's completely saturated with what? Oxygen. But its job is to deliver oxygen anyway, so we know somebody's going to get off the bus. It comes along here. Okay. I'm going to draw one little oxygen molecule getting off the bus, but you know, that leaves some room on the bus. So that's how the CO2 gets on. It can occupy the space that oxygen leaves. Okay. I mean, so that's why the carbaminohemoglobin it's about 25%. I said it was 23%. It's about 25% because of, that's the average room there is on the bus. Okay, the rest has to be dissolved or in the form of bicarbonate. Well, anyways, what I have on this slide here is the Bohr and Haldane effect. Let's remember that the Bohr effect facilitates even more oxygen unloading. Okay? Let me remind you of that fact by writing it on the board. Bohr effect facilitates more O2 unloading. This unloading allows two things. Allows number one, it allows more CO2 loading onto HB. More CO2 loading to HB. That's our formation of the carbamino hemoglobin, HbCO2. Carbamino hemoglobin. I like saying it more than spelling it. It's a long word. Carbamino hemoglobin. So it's kind of like in my bus analogy. Well, if there's the Bohr effect going on, well, more get off the bus, okay? And maybe it's like another guy gets off, and then another CO2 can get on the bus as a result. We get more formation of the carbamino hemoglobin. The other thing you do is you shift this equation to the right more. Number two. Shift this EQ equation to the right. So the equation I'm talking about is this one here. You're shifting it this way. You're trying to get carbon dioxide into the form of bicarbonate because that can be soluble in the plasma. Look what happens on the cell surface. Okay, number one, Bohr effect, more O2 gets off the bus. Number two, Haldane effect. These two things, where I labeled this number one and this number two, those effects are called the Haldane effect. They happen as a result of the Bohr effect. So number one, the Bohr effect happens. That's why I have number one on the slide. You facilitate more unloading, more O2 gets off the bus, so you get more CO2 loading. And you shift this equation to the left. This is the Haldane effect. And basically, this equation here, note the chloride shift. When you get it to the HCO3, the bicarbonate, you shift with the chloride. You're trading basically a negative for a negative. So you get the bicarbonate off the surface of the red blood cell and in the plasma compartment. So when you get to here, you get the chloride shift. Chloride shift moves bicarbonate, HCO3, to the plasma compartment. So this is gas exchange at the tissues. Let's look at a picture of gas exchange at the lung. Everything's going to be reversed. At the tissues, we're dropping off the O2, we're picking up the CO2. For the external respiration at the lungs, it's reversed. We pick up the O2 and we dump the CO2. Let me make a small section for the external respiration. We're picking up the O2, we form oxyhemoglobin, HbO2. And we dump the CO2. Note this, note how the equation goes in reverse, really fast, again, on the surface. So it's like you do chloride shift in reverse. Okay, that puts the bicarbonate on the surface of the RBC where the carbonic anhydrase is. Just goes this way, form carbonic acid. And then that dissociates into CO2 plus H2O. Put my carbonic anhydrase right there. So that's what's on the slide. And the goal is now we're trying to get the bicarb back into the form of the gaseous form, the CO2, so it can be extracted from the blood into the alveolar space so you can expire. Breathe it off. I included one slide to illustrate the effect of the Haldane. But first, it's Bohr effect happening first. The factors that affect more O2 unloading, that's the Bohr effect. But the O2 unloading, that influences CO2 loading, and that's the Haldane effect. So all you really got to understand about this is the light blue line is when hemoglobin is not saturated. They say 0%. That just means at any value of partial pressure CO2, you can get more CO2 into the blood because hemoglobin is not saturated. That's all this graph. That's the only reason why I included it. But what happens first? Bohr. And as a result of that, Haldane. So to review that concept, let's start with these parameters that shifted the equation. So in your notes before I erase this, I'll put a number 1 next to Bohr, put a number 2 next to Haldane, because that kind of like happens as a result of Bohr. Trying to wrap up here, but let's think about the Bohr effect in terms of exercise. What did we say about pH during exercise, up or down? I heard both. The blood gets more acidic. So that means the pH drops. Yeah, more acidic, so maybe you're thinking of more acidic, but pH drops. Yeah. Okay, carbon dioxide. What happens at that value when you exercise? Goes up. And what have I got next? G. Up. What about body temp? also, and these are all the things that happen with exercise. And what I had said was, let me advance my slide. Come on. So those four things, I say A, B, C, D. Okay, these four things. How they change during exercise. How do they shift the curve? Which one is correct, the A or the B? I heard both. B is correct. Shift it down to the right. So basically, if this is normal, these things shift it this way. Okay, that was the rightward shift I was talking about. All right, so then again, we still have our four parameters. We shifted rightwardly. Now I answer this. So these things, A through D, how would you answer it? Do they facilitate more oxygen loading or unloading? And then what effect is that called? Which of these choices is correct? It facilitates more unloading, and we call that the Bohr effect. Keep that down. So this shift means increased O2 unloading, called Bohr. As a result of this unloading, we get carbon dioxide loading. What effect is that? Two choices. That's Haldane. Okay. As a result, get Haldane. This one?
Yes.
Sure.
So the graph is B. It shifts to the right.
That's correct. The dotted line.
Yes, the dotted line shifts to the right.
Mm-hmm.
But when you have here to the left on the slide, it says A rightward shift, B leftward shift.
Oh.
So I was confused.
I'm sorry. I always do that. Pretend those aren't there. It's rightward shift.
So it is graph B, and it's a
graph B.
rightward shift.
And it is a
correct?
right. Yeah, when I did the automatic label it, I should have changed it to like numbers, not letters.
Okay, I just wanted to make
Glad for
sure
catching that. I
I'm
never saw
understanding
that.
it correctly.
Any other questions? I put some questions at the end, and I always do this to make sure I covered everything. And what I realized from the morning classes, I didn't present number 7, so don't worry about it. I'll make sure that question's not on your pool of questions for the online proctorium test. And let's remember, when does that test due? Tuesday, so you guys got that straight. It's 50 questions, randomized, and it's all set to go. And yeah, I didn't plan a lab for today because I wanted to give you guys some time in class to ask questions after this lecture because, you know, Monday's a holiday, so you're not gonna meet. It's better than today. I'm not gonna see you the next week, Wednesday. I will be in my office after class, but if you have questions now, you can stay and ask me. If not, you're dismissed. Or you can, what's that? You're not coming Monday. What? I'll be here.
So
You just said you would be here Wednesday.
Oh, okay. I did? No, I said I won't be here Monday. I meant to say that. I'll be here Wednesday, just to be clear.